So let's start the talk. Welcome everyone, my name is Istvan Rath, and first of all I would like to thank you all for coming to this very late session today. I'm trying to be as quick as possible in order to allow you to leave home as soon as you can. So the talk is about lessons that we learned from building Eclipse-based commercial add-ons for commercial modeling tools. Specifically, as you will see in the presentation, the tool platform that I'm going to talk about is MagicDraw. But the focus of the talk is more on the technology side than the business side. So I wanted to make sure that this talk is more of technological interest to tool providers rather than talk about the commercial aspect of an endeavor like this. So how many of you know MagicDraw? Hands up. So for the rest of the audience, MagicDraw is basically a popular UML SysML modeling tool. It has been available for a very long time now, and it's used by a lot of users in a lot of countries all over the world, in industries such as avionics or defense, aerospace, automotive, energy, telecommunication, and so on and so forth. And it's basically a standards compliant but also extensible platform. By standard compliant, I mean that you can use it as any other UML SysML based tool. And by extensibility, I mean that it caters to developers of add-ons as well. So you can actually develop plugins for MagicDraw that add functionality to the platform. What's very important to note is that nowadays, especially, this tool suite is not just a modeling tool anymore, so not just a plain desktop application, but actually an entire suite of technologies that provide solutions for not only authoring models, but also running simulations on them or analytics tools on them. And Magic also has a solution for supporting collaborative work nowadays more and more on the web platform. The technology that is of particular interest to us in this talk is called Teamwork Cloud, which is the collaborative backend for UML SysML modeling. In particular, you can think of Teamwork Cloud as a kind of a version management system like Git or SVN, but more tailored specifically for models. When you think of MagicDraw, you typically think of a commercial tool that is supported by one particular vendor. But in the case of MagicDraw, this is a little bit different, specifically because of the open nature of the platform. So there are not only commercial third-party add-ons to this tool, but also open source add-ons. And on this slide, I put the one which is the most interesting and important, in my opinion. It's called OpenMBEE. How many people have heard of OpenMBEE before? Hands up. Yeah, much fewer. It's not that well known in Europe. But over in the US, it's much more well-known technology. It's an open modeling platform, which is actually not just specific to MagicDraw itself, but it contains a lot of bindings to other tools like Mathematica or MATLAB or OSGi or many others. But it's sort of still heavily relies on MagicDraw because the majority of the modeling, which is done, in toolchains centered around OpenMBEE happens in MagicDraw. And in fact, there is an open source plugin developed by folks at Jet Propulsion Laboratory over at NASA, which is called MDK. And it's one of the most fully featured modeling solutions available as a third-party open source add-on to MagicDraw. All the code that they develop is available on GitHub under various rather liberal open source licenses. And over the course of the developments that I'm going to talk about, we've come to realize that this code base is actually a source of a lot of very interesting and useful and reusable assets. So if any one of you are interested in exploring this topic more deeply, I definitely suggest you to check this out because it's very interesting also from tool developers' point of view. And MDK is a very good example of an add-on developed around the open API extensions of MagicDraw. So this document here, this open API specification, is basically the technological key to all of the things that I'm going to talk about later in the talk, because this specifies how to create add-ons for this platform. So the products that we developed, I'm going to talk a little bit about so that you understand the general context of this work and why this is important to us. These products and concepts are called IncQuery, specifically IncQuery for MagicDraw and Teamwork Cloud. And so what is this technology? It's basically something that we develop with the overall goal of establishing a new generation modeling platform for cloud-based solutions, specifically with scalability as a primary concern. So IncQuery is basically meant as a scalable platform for running model queries and transformations. So essentially the basic building blocks of modeling tools in a scalable way, in a collaborative scenario. And IncQuery provides not just a platform, but a specific language, or more like a set of languages and APIs tailored specifically for working with models. And basically the most important end user scenarios that we are aiming at is enabling validation, structure analysis, and other analytics features over systems engineering models and domain-specific engineering models and AutoSAR models and many others. The heart of the IncQuery technology is an engine which I call hybrid database engine. And by hybrid database, I specifically mean the fact that it not only relies on a persistence mechanism well known from database technology, but also an in-memory representation which allows the high-performance operation of the query and transformation engine. So at the basic level, IncQuery interacts with MagicDraw and Teamwork Cloud, but many other engineering data and modeling storage platforms as well. And it basically accesses their contents through interfaces which conform to modern interface specification technologies like OpenMBEE and Swagger. And based on this access layer, it builds a persistent index into its own database, which is based on a cloud-based clusterized database technology, from which it can instantiate in-memory shards on demand whenever there is a need, either from the user side or a tool side, or a particular workload necessitates this. And in such an environment, which is actually architected around clusterized container infrastructure, we can achieve up to 1,000 times faster performance for queries and transformation than what is typically achievable with traditional databases, and in a horizontally scalable way. Obviously, that's the most important thing, because this cloud context allows this technology to scale with the number of users as they are growing, and obviously the complexity of the workload that the tool is putting on the system. So this technology is specifically aimed at thousands of concurrent modeling users putting heavy load on a modeling infrastructure, which is more and more the case in complex systems engineering scenarios. For example, at JPL, they have, let's say, 500 concurrent users from different parts of the organization, and they are working with SysML models which are more than 1 or 2 million elements in size. Obviously, a repository can be much bigger than this. So if you think of consecutive revisions, then you can easily get repository sizes of 100 or even 500 millions of elements. This is the range that we are aiming at to handle efficiently. Just to give you an idea of what are the typical usage scenarios that this technology can cater to, obviously the most important one is model analysis or validation reporting, which I already more or less described to you. It's a kind of a fine box style of service, but for models, which is obviously very important for practical purposes. But with these powerful queries, you can do many other very interesting things, such as change impact analysis, which is a very frequent problem in a collaborative organization where there is a lot of dependencies between models. An impact analyzer can determine, the potential effects on downstream projects, things that have direct or indirect dependencies of what I'm working with, whether I'm messing up the work of some colleague, maybe someone I even don't really know about. So this is something that an efficient query engine can support very nicely because it allows us to realize such a logic in a pre-commit hook. And finally, and maybe most importantly, IncQuery also has support for ad hoc style of querying, so kind of an exploratory analysis over models, which is more and more important, especially because of the complexity of MBSE and systems engineering in general. Just to give you an idea of how this tool looks like in practice, I included a couple of screenshots. This is how this tool looks like within MagicDraw. So we actually realized this first and foremost is MagicDraw plugin that you can interact with within the modeling environment, specify queries, run the queries, debug them, and so on and so forth. But the server is also available to tool developers and programmers. So it provides a set of APIs over web standards compliant interfaces and technologies that are very easy to integrate into a custom application. So the screenshot that you see here is of a tool called Swagger, which we use to expose the business logic functionality of this server to tool developer, for instance. For end users, you can build powerful web applications based on such a technology. For example, here is a screenshot of a web application that we realized with a framework called React. It's very easy to interface with OpenAPI specifications from modern JavaScript frameworks. So very powerful collaborative modeling tools for the web can be built on top of such an infrastructure. So this is the context of the lessons and basically the rest of the talk. I just wanted to give an overview so that you understand. And now I'm going to talk about the lessons that we learned while developing this technology. So first and foremost, it's very important to note that this IncQuery framework is built on a lot of open source components, many of which are originating from the Eclipse ecosystem of tools. Primarily, the engine itself, which runs inside this hybrid database technology is called VIATRA. It's an Eclipse open source project, and it's essentially a model query and transformation framework. And it has been integrated over the years to a lot of open and commercial tools as well, such as RTOP or Papyrus or Capella. And there is a lot of industrial users already, some of whom actually contribute and help us in developing this technology further. Other than this, the technologies that I would like to mention here are Vertex, Eclipse Vertex, and Eclipse Collections. Collections is obviously a low-level component in this technology, which provides us with data structures, efficient memory-efficient data structures. But Vertex is also kind of at the heart of this technology. It's a very new and very useful and very powerful library. How many of you know Eclipse Vertex? No? It's an Eclipse project, actually. And it's a framework for reactive programming. It's a kind of an ACA, implements an agent or asynchronous computation model, and it allows us to build a Java application on a microservice architecture, which is very easy to scale if the load on the server increases. Finally, for the backend, we are using Apache Cassandra, which is one of the best distributed NoSQL databases which are available today. At this point, I would just like to give a little bit of a sneak peek into the story of the VIATRA project, because this is something that we've been developing in tandem with this work. So VIATRA will be available in a major new release, 2.0, in Eclipse Photon, which is out in a few weeks. And it contains a lot of improvements, both on the language level and also the runtime level. And actually, some of the runtime improvements, such as the native usage of Java 8 facilities, were key for us in order to allow such a scalable execution over a cloud-based platform. Going further, so one of the reasons why we chose MagicDraw to be the context of this development was the observation that it uses EMF under the hood. So inside MagicDraw, you have Eclipse Modeling Framework compliant interfaces for representing and working with the models. However, this EMF implementation is a little bit customized. First of all, it uses a completely different meta model for UML models than what MDT or Eclipse UML does. And in my opinion, it's actually better in many ways. First and foremost, from the point of view of support for profiles. So profiles have traditionally been very difficult to work with in Eclipse UML. It has been improved over the years, obviously, but Magic has decided to pursue a completely different approach to representing profiles. And it turns out that their approach has a lot of implementation benefits which allow easier maintenance of related code. The second lesson was our kind of a surprise to us that this EMF implementation in MagicDraw is a custom implementation. So there are no actual vanilla E-objects in the background, but a lot of extra logic centered around memory management, making sure that large models can be stored and managed by the tool in the most efficient way. However, it's not 100% compatible in every corner case scenario with the EMF itself. So there is a couple of, let's say, cases which need a little bit of adaptation, and the open source contributions that we created during this development actually help with identifying and working around this. Specifically, by the open source contributions, I mean a new project that we put on GitHub just a few weeks ago. It's called V4MD, so VIATRA for MagicDraw. It's basically the open source glue code released under the version 2 of the EPL that shows how to bind an EMF specific tool such as VIATRA by default to MagicDraw. And what's very interesting is that this is itself deployable as a MagicDraw plugin on which your own plugins, should you decide or want to write one for MagicDraw, can depend. So this is something that is directly reusable in case you want to experiment with this technology. The second very interesting lesson that we learned while working with MagicDraw is how it relates to OSGi. So they shifted to an OSGi-centric overall design in the 18 series of MagicDraw. However, this OSGi approach is completely different to what Eclipse actually does. So one of the major lessons that we learned was that these MagicDraw plugins do not correspond to OSGi bundles the same way as Eclipse plugins do, meaning that there is no separation of class path similarly to the OSGi mechanisms. And also the dependencies are handled completely differently. So coming from an Eclipse plugin developer's perspective, this is a very crucial difference that you have to pay a lot of attention to in case you want to avoid having a lot of technical issues. One of the things that I would like to point out relates to the usage of plugin XML files. MagicDraw plugins also use plugin XML files, but these are completely different files than Eclipse files. So if you are specifically using Eclipse as your IDE for developing such plugins, you have to make sure that you do not try to open these plugin XML files with the PDE editor, because it will just get errors that you will not probably understand at the first try. So this is something worth watching out for. For those of you who know our VIATRA framework, you might be aware that it uses Xtext for managing its DSL for specification of model queries. So one of the things that we wanted to experiment with was how to integrate such an Xtext-based editor into a commercial application which is not based on, or not entirely based on Eclipse technologies. Obviously, Xtext itself is architected in a good way in the sense that a lot of the things that it provides are easy to reuse and package, like the parsing infrastructure, which can be deployed basically as a standard application. But if you want to integrate a full-blown editor, which also has a lot of UI Eclipse dependencies, that's a lot more tricky. In the case of MagicDraw, the entire UI of the tool is based on Swing. So embedding an SWT-based component into a Swing application is something that we experimented with, but found it not to be practical for real-world scenarios because of technological issues that date back, 10 plus years. So in order to work around this issue, there were two major alternatives that we considered. One of them was to go for a very modern approach, use this language server protocol technology, which appeared in Xtext maybe about 2 years ago. But there was another, let's say, alternative, which meant to separate all the Eclipse UI specific contributions in an actually a separate kind of a companion application, and then somehow make the two apps work together. And this second one was the one that we ended up doing, and I will try to explain to you why. How many of you know LSP, or Language Server Protocol? Okay, that's good. So LSP basically allows us to separate the front-end part of a text-based application from the back-end part of a text-based editor. However, so on the back-end part is called a language server, but this is something that you would still typically deploy within your desktop applications for technological reasons. However, deploying such a server at the moment, especially for Xtext, brings some dependency issues which are hard to work with in the MagicDraw context because of this class path handling issue. So this was one of the major difficulties that pushed us into a different direction. Another one was the observation that up to this date, unfortunately, no mature client for Swing exists for LSP, and in my opinion, this is not likely to change in the future. So what we were actually experimenting with is to reuse the embedded web browser found in MagicDraw, and you can do this in many other tools as well, and use a web-based editor front-end like the Monaco editor in conjunction with the LSP protocol. However, this embedded browser is still based on a rather old version of Chromium, which has some issues with this Monaco code base. So this is also a kind of a showstopper for now for this path of integration. So the alternative solution that we came up with was to actually develop a completely different application, which we call a companion app that will work in tandem with the host. And this companion app will be based on RCP, which solves the UI integration issues, also the dependency issues. But there needs to be some kind of communication going on, obviously, between the two applications, which we solved in a rather low-tech way. So this window that you have actually seen in the screenshot that I showed previously is not a model dialog over MagicDraw, but it's actually a separate application which disguises itself as a model dialog that is built on Eclipse RCP. And the interoperation between MagicDraw and this RCP application is done with Java remote method invocation, essentially. In the future, though, such an architecture can actually host a proper language server, which allows us to reuse this work in other contexts as well, like making it work together with VS Code and other LSP-compliant front-end platforms. This is how this application looks like from the close-up. So it's actually an embedded Xtext-based editor, which is actually very useful also in this SysML systems engineering world, because this language gives you very direct access to things like the SysML profile. So using this language that we provide, it's very easy to hide the sort of the ugliness of the meta model, and it allows the systems engineer to reuse compound concepts like a SysML block with just one line of code within a model query. The final lesson that I would like to talk about deals with how to build these plugins. This is usually a rather painful issue, especially if you are a tool developer, you know this. So this is again an area where this ecosystem is completely different from what we are used to in Eclipse, because many of the standard aspects of building are not that well elaborated as with Eclipse nowadays, especially when we are talking about collecting dependencies, executing new instances, managing of third-party external dependencies, and handling generated code. These are all things which kind of have to be done manually. However, happily, this OpenMBEE project has provided us with a very elegant solution framework, which is built on a modern build tool called Gradle. How many of you know Gradle? Yeah. So Gradle turns out to be a tremendous help in this respect, because many of these aspects can be covered very nicely by this framework. And I'm not going to talk about the details now, because it's probably not that important. What I would like to mention, though, is that we actually open sourced a plugin skeleton as well on our GitHub, which is just a Hello World plugin, so it doesn't do anything, but the build configuration is there. So if you check this repository out, it should give you an idea of how this actually is built up, where to add your own stuff, so you can get started very quickly if you want to develop a plugin on your own based on this skeleton. And in fact, V4MD, for example, the plugin that we developed is also built using this approach. During the course of the developments, we made some further contributions to the open source community around MagicDraw. I would just like to highlight 3 more components. There is a benchmark available on our GitHub, which contains a complete end-to-end automated framework that can be executed in a continuous integration build environment in order to carry out automated scalability and performance measurements. For these performance measurements, we actually made use of a model that was originally contributed by NASA JPL. It's called the TMT, or 30-meter telescope model. It's a real-world large SysML model that contains a lot of details in a standard format. And all the scalability evaluations that we do in an automated way are actually based on variations of this model. And it's probably also very useful to tool developers for functional and non-functional testing purposes as well. And finally, we created a fork of MDK. So MDK, again, is a component of OpenMBEE developed by JPL in order to demonstrate how to use V4MD within such a project, so how the APIs work and how the build system works. So now getting to the conclusion of my presentations, the main takeaway for the talk today are, first and foremost, our experience has shown that integrating with proprietary tools is obviously much more challenging than what you would have compared to a purely open Eclipse ecosystem, for instance. But there are already a lot of very useful and open source tools that make your life easier and easier in the most important aspects. What I would like to stress further is that NoMagic is actually a very open and collaborative partner. So many of the things that we have done have been carried out with their support, and I would like to thank them for this. And as a result of this approach, there is actually an open system, open ecosystem around their tool, obviously on a much smaller scale than Eclipse, but with a lot of value that is worth exploring and also contributing to. So this is what we ended up doing. I would like to invite all of you to watch out for this new VIATRA release and also the server. If you're interested, we are very happy to give you further details and demos. And if you want to try this plugin yourself, it's actually available at that URL, which you can also navigate to using this QR code if you would like to use your phone for that purpose. And it's actually a fully featured trial available on our website. So for any of you who are actually interested in this technology, you are very welcome to try it out. And with this, I would like to thank you for your attention. And if there are any questions, I'm more than happy to answer. Are there any questions?